Yes.
We need some help in the PLC because some person who wants to try to take a test for 111, for Math 111 has walked in and we said, sorry, we're closing, it's not a good place to take a step, and then take a test, and she was like, it's okay, I'll just stay here. Like, no, you can't, and she's like, yes, I can. So we're trying to tell her that the PLC is closing, and she's just not leaving. So we need, and she's not listening to us.
Which room?
The PLC, the Physics Learning Center.
I know where it is.
The 304.
304.
Yeah, she's just, we're not allowed to leave students in there, and we're supposed to be leaving there.
Okay, so supposed to close the door, right?
Yeah, and she's just not leaving.
Try to check with either Matthew or Janty.
Okay.
See if what do they say, then you say. If ever you just leave it. Okay, thank you.
I'm aware of that senior edition, but I don't know. But
You'll get a good vibe of.
Great.
Yeah. Yeah.
Yes. Yeah, yes, yeah. Thank you.
Oh.
Thank you. study. Let's study. Let me check. Okay, you put the second three. Okay, because now flip for what was his name? A little longer. Saraga. Okay. I just remind what we discussed from chapter 2. We introduced the Hamilton's principle, and the Hamilton's principle. I just try to remind you that the condition, right? The monogenic means the force can be written as this. There is a scalar function such that is or potential field, whatever the force be has a relation to derivative from there, and the constraints be holonomic. So if these two conditions satisfied, we introduce this line integral for the Lagrangian, and then according to the Hamilton's principle, it derives Lagrange equation, right? But here, the GF from 1 to n, these are all independent. I mean, we select these general coordinates are all independent, then this equation is satisfied. Now we extend Hamilton's principle to the case. Again, same condition, similar is holonomic. But now, we do not restrict our general coordinates are independent. You can select any if we want to describe system, even though they dependent, don't worry. So in that case, we introduce here a multiplier, right? Multiplier, lambda alpha. Then we apply this Hamilton's equation, we found this formula, Lagrange equation here is not equal to 0, this is equal to 0, because in dependent, right? So we have another term we call this general force, and this general force equal to this. So you can see here, since we introduced this one related to the constraint, this force is the force associated with the constraint. So the advantage of this one is, first, we don't need to worry about how to select this independent. You have to count how many degree of freedom and you're going to select independent general coordinates, right? That is in this case. But in this case, don't worry that. You just select the coordinates as you want to describe. Second, we can also obtain information about force due to the constraint. Here, you cannot get anything, right? So now we do one example here. We keep continue. I think we start this one last class, right? So this is a spherical that just put this down, this Earth, right? So what we know is, first you analyze this, right? So that definitely the force is gravitational force, right? Force, and we know that speed satisfy this. So then the constraint, right? In this case, we only have one, right? It's r minus a equal to 0. Because the particle always move out on the surface of this sphere. Of course, it's considered before they leave, right? Before the particle leave the surface, always satisfy this, right? So how many? You don't need to count how many things. We are not worried about how many the independent of general coordinates. So we don't need. In this case, we need to understand how to determine n, right? Here, we don't need to do that. We just set up as possible as we can these general coordinates. The equation of constraint. So yes, satisfy this condition, we can go to here. Okay. So the first one, usually when we have this one, I'm going to give because we are going to use this equation, so I'm going to give a number. Equation 1. From equation 1, you can also get this r dot is 0, right? Because r equal to a is a constant, so r dot 0. So this is another information from 1, right? Okay, that's from this. Let's give you this one. Okay, that to keep in mind. Then now we go to the further. So now, since we do not worry about how many independent general coordinates, so we select general coordinates as what we want. So I want to select R and theta. Even though we know actually only one independent, but I select two as my general coordinate, so they depend. Right, they depend, that's fine. Okay, once we select this, so then we know, and this is any case xz, right? It's just move along this xz plane. So x is R sine, right? Sine theta, and z is R cosine theta. I think we reach to here or next step, right? So then you can do immediately x dot is R dot sine theta plus theta dot R cosine theta, and then I want to okay. I want to finish this one. I want to discuss R dot cosine theta minus R theta dot sine theta. Here, even though we know this, but I want you to put here because I want you to put the general coordinates and general velocity until you write down this equation, since here we need this one. If you immediately write down that 0, you miss one of the equation. Okay, so keep this one, even though we know that's 0, let's keep it, okay? And then so now this one, the transformation equation, now we can write down the kinetic energy is just a half of mass, right? And x dot square plus z dot square. And in this case, you just submit this one. So you will see that, okay, I think, you know that is R dot square plus R square theta dot square, right? If you put it together. And this potential, okay, mg, mgz, right? If we select the potential equal to 0 at this z equal to 0. So any position is mgz. So then Lagrange here. Here you either use this R cosine theta, right? If you replace this xy by this R and theta. Okay. L. So L is half of this one, right? Half of, okay, sorry, this half. Half m and R dot square plus R square theta dot square and minus, right? Minus V, which is mgr cosine theta. All right, so once we write down here, we are going to apply this formula. And here, depending on G, we have two, right? G1 is R, G2 is theta. So you have two equations. So now let's do one by one. First, for Q1 equal to R, I'm going to say that is the first general coordinate. Then let's first, since we are going to apply this, we need first do the partial L, partial QJ dot, partial L, partial QJ, and this each term. Then we put into equation, right? For this one, partial L, partial, sorry, QJ, so that is R dot, right? Which is here M R dot, right? And here you're going to write 0. Now we know the R dot is 0, right? So that is case. Then partial L, partial R. Do we have R? We have R here, right? Minus mg cosine theta. Then here, partial F, partial R, right? Here. Sum of all alpha here, we only have 1, so alpha equal to 1, right? So we only have one equation constraint. So partial F, partial R. F is where? Is here. So what is equal to 1, right? Now you are going to substitute into this formula. Here, partial L, partial R dot, minus partial L, partial R, equal to, I'm going to use lambda since we have only one equation was constant, right? Partial F, partial R. Okay, now we substitute. So here, this one is 0, right? So for 0, this one 0, and I think I missed one term. I have another one. Sorry, this one is 0. Okay, I have another one here. Right? Sorry, that is I missed. M R theta dot square. Right? There's R here too. Okay, so now I'm going to sum it. So this one 0. Okay. So partial R and minus here. This one minus that's minus this M R theta. Sorry. Yes, M R theta dot square plus here minus plus mg cosine theta equal to, here is 1, right? Sorry, here's lambda. Because here is lambda multiplied partial f, partial r, partial f, partial r is 1. So now I'm going to give the equation 2. Then you see this is the equation for r. Right, finish. Now let's go to the second one. For Q2 equal to theta. Partial L, partial theta dot. The second term is mr squared theta dot, right? And the partial L, partial theta is here. It is plus mg theta dot. R, right? Let's keep R. So I have R, keep R, and theta dot, and sine theta, right? Only this term. And partial F, partial theta. Do we have a theta? F only function R, right? So that is 0. Then we are going to substitute into this formula. D is the Lagrange equation, partial L, partial theta dot, minus partial L, partial theta equals to lambda, partial F, partial theta, right? So now let's substitute. Partial L, partial theta dot is this one. But now, be careful. Total time derivative, so R, in general, is also time dependent, but we know that is 0, right? So in this case, you can either keep this one. So now, if I want to make this so in later if R change. So now let's first do this one, right? So 2R and then 2M R dot theta dot plus mr squared theta double dot, right? Is this term total time dt, suppose, and minus this term mgr theta dot sine theta equal to 0, right?
That's the level del theta. We take derivative in terms of theta, so we can write R theta.
Sorry, you are right. Yes, that is not R. Just sine theta, you are right. Not this. Just this one, right? Okay, you are right. Here, there's no this term. Now R keep, right? We have R, right? We have R here. Just cosine becomes sine, yes. Okay, now you can substitute here. Equal to 0 from equation 1, right? Give us this equation 1. We know this. So now you can reorganize this term 0. So we have mr squared q double dot. If you want to move the order, just keep here mgr sine theta equal to 0. This is equation 3. So now how many equations? Equation 1, equation 2, and 3. How many variables? Unknown variables? R, theta, and lambda. Right? So we have 3 equations, 3 unknown variables. Yes, we can solve this. So now, let's do, since R here, in principle, is also constant, all right? So from this equation, the function theta. So let's do this one. So now I solve equation 3, right? M cancelled R, so we have a theta double dot equal to I move the r over g sine theta, right? And if you now you want to replace r by, that is equation 1, the equation of constraint. So we have this. Okay, so from here, this is a second order derivative, and then that means d theta dot dt equal to g over a sine theta over d theta dot okay. I'm going to do this way. D theta dot, let me first count here. So that is g over a sine theta dt, right? Then I'm going to d theta. So here, that is g over a sine theta dot, right? D theta. If we do this way now, we have move this theta dot to this, so I have a theta dot, d theta dot equal to g over a sine theta d theta. So both sides independent, so I can do the integral here, right? So that is some mathematical technique that you want to replace the variables such that you can do next step is integral. So left-hand side is half of theta dot square equal to, here we have a over g and cosine, right? So minus cosine theta plus some constant, because this is a indefinite integral, right? So we need, so we have this one over theta dot square equal to minus, okay, 2g over a cosine theta plus c. So now we have this one, and then I think I didn't get, but you remember last time I have the initial condition, right? So v when t equal to 0 is 0. That is initially at this case, right? And we have very small force to kick off this one. So then after that, no any other force. So that is C here. Then the cos theta dot equal to 0 at the t equal to at the initial, right? Did I? Okay, theta equal to 0 case, let's do this way. T equal to 0, theta dot is 0, and theta also 0, right? We select it here. This is the initial, right? This is the initial. We now equal to 0 at this place. So we have this condition. Therefore, now here, when you set 0, this is a C, cosine 0 is 1, right? So C equal to 2g over a. Then we have the formula for the theta dot square. I think that's. So finally, we have a theta dot. Let me just write down. Theta dot square is, if I open C over 2g over a and 1 minus cosine. Theta over theta dot is square root 2g over a 1 minus cosine theta, and this one is d theta dt, right? So you have from here you can see the d theta 2g over a 1 minus cosine theta equal to dt, right? Then you do the integral in principle. You do the integral, and here you will have some function of theta, and that equal to t minus t naught. Then you are going to inverse or reverse, whether reverse. This is a theta function, t as function theta, right? So then you're going to make this. This is give you t as the function of theta, then you are going to make theta as a function of t. That is also math, so we will not spend time here. Just let you know when it's doable, but the remaining part, how to take integral and then get this one and do. That is sometimes is not easy, so but we know that is doable. So that is the solution. Find the equation of motion, right? So that is the angle as a function of time, right? So now we are going to see, I think there is another critical. So we know, all right, yeah, that is, okay. That is another lambda, right? Because R, we know that is. So the lambda, now we are going to solve for the lambda. Okay, so that gave you an equation of motion. We answer the first question. So usually for our class, either you reach to here or here, which is okay. I don't need, of course, if you can do following, that's good. But at least up to here, that is what we focus on. That when it's asked her to find the equation states, give me this equation, that means okay. All right. So that is, now we are going to solve the lambda. The lambda is from this one, right? Equation 2. So the lambda, let's go, the lambda is from equation 2. Previously we solved this from equation 3, right? Now we back to equation 2. So equation 2 lambda equal to, okay, minus m r theta dot square plus mg cosine theta. Now theta dot we already have here, right? Theta dot square. So you substitute that minus mr 2g over a 1 minus cosine theta plus mg cosine theta. So you have this r cancelled, right? Because r is 8. So you have 2g, 2mg. This is mg. This is negative, negative plus, right? So you have 3 of mg cosine theta, right? I think I can erase this part. I need this curve. So the lambda equal to, now I'm going to reorganize. Lambda finally is mg 3 cosine theta minus 2. Right, because we have take mg outside, so this is a 2g, right? So there's a factor 2 here. This one you have a 2 negative cosine, negative can plus, you have 1, so that is 3 here. All right, so that is lambda. Then now we are going to discuss lambda. What does mean lambda? Okay. Lambda equal to 0 if when the cosine, there's a particular, I'm going to say stop, the particular angle equal to 2 over 3, right? So you can see here, if this one cosine theta that equal to 2 over 3, then 3 cancel, 2 minus 2 is 0. So that's the case. So what does mean? There's a critical angle here. We call it critical angle. Such that, what happened? Suppose this is a critical angle here. And above that, after that, the particle will leave out of the surface, right? The particle will leave out of the surface. I think I can erase this part. Right? That gives us this condition. And then in any case, that is 0, not 0. Larger 0 if the theta is smaller than the critical angle, right? So if this one is smaller than this larger number, right? Theta cosine theta 0 is 1, right? So that is from 3 to some numbers, but if this angle is smaller than this, it's moved on the surface. If move on surface, there's lambda this lambda value is non-zero. Then now we are going to discuss what this means. What is lambda? Okay, so that is lambda. We discussed this. We introduced this the multiplier. Now the question is, what is physical meaning of this, right? So. So, now that means, now let's look this. Remember we introduced, I erased that equation with this extending Hamilton's principle. The Lagrange equation at the right hand side is this one, right? That is, let me write that in general, alpha alpha. Now I'm going to use m. Previously we used k, the total number of equations of constraint. Since later we are going to use k index, so now I'm going to replace k by m. This is what we know. That is given as a general force associated with the force of the constraint, right? So here, because this now, in this case, partial f partial lambda is 1, right? So that is equal to 1. That means, so lambda equal to mt 3 cosine theta minus 2. So that is the force due to the constraint. Now let's look what type of constraint. So here, this one is lambda is correspond to r, right? Is for r. This is a okay. This qj is r, right? So what that means? So this is the GS component, and GS components around radius is r. So the force okay, let's see. I'm going to instead of G, this is I'm going to replace this QG equal to R. This radial part, right? So the directions along this direction and this constraint, what is constraint? So this constraint change with the angle, it decrease until 0. So this one we know it is the normal force. Particle touch on the surface, and surface give a reflection to support the particle move on the surface. That is normal force, right? That makes sense? So that is constraint we know because the constraint is constraint the particle move on the surface. How to do that? Support the particle. So how to do that? That is particle. If you use Newtonian analysis, you know this empty gravitational force. Now you project two parts, right? One is move with the motion along the tangent surface. Another is this one. And this, according to Newton's third law, action reaction. So the surface will generate the force along this radial arc. That is the support particle do not come into the surface. That is the constraint we introduced. People remember. That is come from. So you see here the advantage of this extended Hamilton's principle can help us. One is we do not need worry about this to show the general coordinates must be independent. Second, we can analyze the force due to the constraint. Okay. So next example, even though it takes time, but I still want to make more exercises. This example is we have did before in chapter 1. We want to revisit, but I just plot the figure. I will not write down sentence. You know that is. Remember this. We have a wire, uniform rotate omega t equal to theta. So this is r. We will define this particle here, right? This a bead. This is a bead. Move along the wire, and the wire uniform rotate, right? This is the problem which we are going to revisit. So that anything a bead moving along a wire which uniformly rotate. So we are already solved equation of motion. In that time, we know with just only one independent general coordinate, we select one and we do the others. But now we are going to revisit this problem. We are going to solve. One is find one equation of motion. Second, force due to the constraint. So now let's do the solution. We are going to solve this. Okay. First, we know this is on the plane, right? Potential is 0. And then there's no any other force, right? So we know that it satisfies the Hamilton's principle. The partition is monogenic. So I will not write down the details. So here, okay, let's constraint, right? Constraint, just write down the formula here. So what is constraint of this f? We already know this for x, y at any time. So y to x equal to tangent, right? So that it means minus tangent theta equal to 0, right? Or I can write this way, tangent theta, which is minus tangent omega t, right? Equal to 0, since theta equal to omega t. So we have this equation of constraint. That is only the equation of constraint we have. So we have this is a holonomic, yes. Then we can apply the extended general coordinates. So first we're going to select this one. To select this one, as we say that we will not worry about whether they are dependent or independent, so we select to describe this one. The system is easy that we are select R and theta as our two general coordinates. And here for theta, this equation, if you use 1, you have this. Okay. So now, when we have this, then the equation will state x is r cosine. Okay, yeah, I think cosine here. I'm going to use theta. Y is r sine theta. Even though we know theta equal to omega t, but as I said, do not do that, replace that here. Because then you assume omega is a constant. That makes some mistake doing it. So let's keep this one. Then x dot is r dot cosine omega. So cosine theta minus r theta dot sine theta. And y dot is r dot sine theta plus r theta dot cosine theta. Okay. So with this, now we can go to the write down the Lagrange. Okay, direct write down this Lagrange. Just jump or combine two steps into one. First one is kinetic energy dot square, and potential energy is 0 since minus 0. Since we select this plane 0, right? This is a plane, not vertical. Okay, so that is only kinetic energy, and then we are going to substitute this one here, half of m. To save time, so now I'm going to, because we know this is a polar coordinates, right? R dot square plus R square theta dot square. And yeah, let me keep here. So now this is Lagrange. Now we're going to apply this equation of Lagrange equation for the extended Hamilton's principle. That's first for R. We have two variables, right? Let's consider R. partial L, partial R dot is M R dot, right? Partial L, partial R is here M R theta dot square. And the partial F, partial R is 0. Since here, that's not depend on R, only theta, right? Okay, so with this, then now d dt partial L, partial R dot minus partial L, partial R equal to lambda, partial F, partial R, right? And equal to 0. Okay, let me just this equation now we're going to substitute here. That is M R double dot. And this one is minus M R theta dot square equal to 0. And in this case, you can replace here. That is, you can replace. Now you can replace by omega. M R omega square. Right? That is this case. Now for theta, partial L, partial theta dot. That is why I want you to keep here. If you keep theta dot, not omega, so you have this term. If you keep omega, you always say, oh, that is constant, you miss this term. That is what I found the previous class, the student had this. So now we have M R square theta dot, right? And in this case, you can, even in this case, you can replace now, since next time when you do the dt, d this one, you know that is already constant. So in this case, now you can replace. And now this is the first term. Second one, partial L, partial theta. We have a theta. We do not, right? So that is 0. Yes. Partial theta is 0. And then partial F, partial theta. F is here. This is constant, right? This is does not. So no theta. So tangent theta, you know that is 1 minus tangent square theta, right? You know it's derivative, right? So then we are going to substitute this into the Lagrange equation. Lambda, partial F, partial theta. So now the first one is here. This case we know omega is constant, so theta dot is constant. Then you do the dt, d theta dot is 0, right? So only the r. So the first term is 2m r dot. Here I'm going to use theta dot or you use m omega is fine, right? That makes sense here. Do this d, this term dt, only the r is function time, so the factor 2 r dot, right? So that is this one, and minus here is 0, right? Partial L partial theta equal to lambda 1 minus tangent square theta. That is equation 3. Okay. So now from equation 2, this will this is equation 2, right? I just replace theta dot square by omega square, so this one only function r dot. So we already obtained. So that is chapter 1 we already discussed. So we have r double dot is m r omega square, and that gives us r. R is r naught, if you remember, exponential term, and r dot is just r dot is omega r naught exponential of omega t or equal to omega r. Okay, that is equation of motion. Since that is only the change of this variable along the wire, right? So we have this equation of motion. Now we are going to solve the second one. Try to answer the question. This one, right? So okay. Now we found to look at the Q. Let's use Qj as r bar from 1. Let's write down the more general formula. Then we are going to apply. So for Qj equal to r. So we have a QR, capital QR is lambda partial f partial r equal to 0. No force along the r, the radial part, no constraint. That's why the bead freely move along the wire, right? So yes, no constraint along r. Now we consider the second one, Qj equal to theta. So Qj is capital Q theta, which is lambda partial f partial theta. Did I solve this lambda? I have not solved lambda, right? Actually, this is a lambda. Okay, first is lambda 1 minus tangent square theta, right? Because partial f is this one. So now we need to find the lambda from the equation 3. So now what is lambda? From equation 3, let's look at lambda. So equation 2, m r dot. Okay, let me go. R dot is here, right? It's this one. So, okay, I write down here 2 m r omega. R dot is omega r, right? Equal to lambda 1 minus tangent square theta. So lambda is 1 minus tangent square theta, and then there's a 2 m r square omega square. Then we can, so here is constraint along the theta, which is lambda 1 minus tangent square theta, which is here, so that is 2 m r square omega square. Okay, now what this means? At least we know the direction. This is a constraint along or perpendicular. Yes, perpendicular to the r, right? Because theta, so that is the direction. Okay, so you know that makes sense since that hole is where this beam inside where, right? So that means there's a force. The constraint, the wire is inside this beam. So now inside the wire. So now this term actually is nothing but this top. So now let's look this one, because to understand this, we know this angular momentum, right? Is RPR, right? Linear momentum, right? P. Okay. So that is okay. R multiplied momentum. That's M. PR is R dot. R and PR is MR dot, right? So that is here. M R dot is here, so that is M R square omega. Then the dl dt do this, so that we have 2 m r dot omega. If you understand, it's nothing but this equation 3, this term. And that is, okay. That is to be equal to, so here r dot is here, right? So that is 2 m r square omega square. That should be normal force, not torque, right? Physically. We know physically for angular momentum, then the total time dt for angular momentum is torque. So that is equal to this one here. Then that makes sense. This constraint generates torque, and we know to make the torque so that the bead can make rotation. So you can see here the advantage of this extended Hamiltonian principle. We do not restrict ourselves to select this general coordinates with independent, but and also we can study, analyze what is the constraint or the force due to the constraint, what is the effect. Okay, now let's go to further ask ourselves. So far we discussed the Hamilton's equation, the principle that required the system to be monogenic. One of the conditions for monogenic that is the constraint be holonomic. Now we want to ask ourselves, how about if constraint is not holonomic, right? That is next job we are going to discuss. So how about non-holonomic? Can we solve the problem or system has non-holonomic constraint? Let's find the answer is two answers, yes or no, right? So if a yes is the form we call the semi-holonomic or linear in the generate velocity, no others. For all other case is not. But if this non-holonomic constraint, it is a semi-holonomic, so what is semi-holonomic? We are going to discuss. Or it is linear in the general velocity. It's still doable. So now let's discuss, right? So now we are going to let's consider this non-holonomic constraint is here. This more release condition, this more restrict. This one is among this one. So now let's start from here, but because others doesn't work, so we are going to consider this case is linear in general velocity. So let's consider this kind of general constraint. So we are going to use G alpha instead of F. F, when we write F, we say that is holonomic. So now for this constraint, if it is linear in Q dot, we are going to introduce the equation constraint. We are going to use G alpha. So now, since we have this, that means G alpha is not only the function of general coordinates, F alpha is only a function of general coordinates, right? But here, it also generates velocity. So in general, that is a condition equation of constraint. Then if in linear, that means it is writing in this way. A alpha indexed as a k, but it is function only the general coordinates and time, and multiply the general velocity and plus another term is only function of general coordinates and time. So you see this linear, right? Because this coefficient does not depend on the general velocity, and this is a summation for general velocity from all these the general coordinates, k from 1 to n. That's why I use k here, so I replace previous our definition for k, use m, right? So that is linear, right? So now if we can rewrite, or we can write this constant, equation constant in this way, that means it is in linear. And we are going to deal with those constraints, okay? So for this, that's equal to 0, right? And alpha from 1 to m. Okay, to deal with this, and again, we are going to use the same idea when we derive this extension Hamilton's principle for the holonomic with release the general coordinates to be independent. So similarly, introduce the Lagrange and determinant multiplier. Lagrange and the term multiplier, like lambda. Now, to distinguish that one, that lambda associated with the holonomic constraint, we are going to introduce mu alpha instead of lambda alpha. But here, lambda alpha is a constant. But here, it is a function of time only. Not function of general coordinates, not function of general velocity, only function of time. Lambda is constant. Does not depend on time, does not depend on general coordinates and general velocity. But here, we are going to introduce this. That is basically this. So if we select this, now similarly we define L prime, which is L plus, since that is 0, right? So 0 multiply all the term mu alpha, G alpha, always 0, right? So L prime plus is equal to L plus this one. That's we define here, which we know that again is a function of general coordinates, generalized velocity, and time. Let me see, also R mu alpha and time. But L only function general coordinate, general velocity, and time, right? Only this term depends on mu alpha. So we introduce this, then apply the extension of Hamilton's principle. Which we did before, so I will not go to the details. I just the similar idea, so I give you the result of a critical step. So then that means we have introduced, look at the principle, Hamilton's principle. If I said I prime is the line integral between 1 to 2 L prime dt, right? And that's equal to the line integral of 1 to 2 L dt plus this, okay, line integral summation alpha from 1 to m mu alpha g alpha dt. That's equal to 0, right? Just apply this, and we know this one 0 because 0 integral is 0, and then this one is also 0. That makes sense because this one we already the Hamilton's principle. So now this reach to, let's just give find the result is that's equal to d I prime d alpha, right? And that's equal to the reach to integral from 1 to 2 summation j. So when we do this, do the partial inside all the term is back to alpha, right? So that is okay. J and inside the partial L prime, partial q j minus d dt, partial L prime, partial q j dot. Okay. And then third half q g t equal to 0. This is a dependent, not independent, right? So we cannot immediately say this is equal to 0, but we can separate it into two parts, right? Okay. So this one, if I substitute L prime by this detailed definition here, so I have this term. So that is summation j from 1 to n, and partial L, partial Q j minus d dt, partial L, partial Q j dot, right? That is L prime. We have L, this part and this part. And last, so this part, do the same thing. We have a partial summation alpha from 1 to n mu alpha g alpha partial qj. Something like this term, right? And then minus d dt. The second term of this is partial summation alpha from 1 to n mu alpha g alpha partial qj dot. Okay. So here the summation is still used. Then again, as I said here, this is a dependent, so we cannot immediately say this inside the coefficient of integral equal to 0, but we can separate two parts, right? Okay, the first part, if you remember, the first part for G, we select all the summation G is a summation G from 1 to n minus n. That is, and okay, all the details, right? I did not repeat. That's b equal to 0, so that means that is qg in this case. Qg equal to 1 until n minus m. These are independent. That means among these dependent general coordinates, we know there are m minus, since if this is a we select, and then we have a m equation of constraint. So it's totally this difference that gives us the independent. So now for those independent, according to the Hamilton's principle, is equal to 0. Okay. Either do this way or in general it's integral here. So how many? Qg dt equal to 0. If this is independent, we know, then give us this one. Partial L, partial Qg, d, d dt, partial L, partial Qj dot, and plus partial mu alpha g alpha partial Qj minus d dt partial summation mu alpha g alpha partial Qj dot equal to 0. That is the first part, j from 1 and minus. Yeah, that works since that's all independent, so the coefficient should be dependent, should be 0. The second part is for g from n minus n plus 1 to n. In this case, we are going to choose or adjust, let's say. Even though they are dependent, so we cannot immediately say this equal to 0, but we can adjust the mu alpha, as we discussed before, such that, so adjust mu alpha such that this coefficient equal to 0. Such that, okay, again, all the formula the same, but the different general points. We almost to the end, so now alright. And in this case, J from n minus m plus 1 to n. So we combine those together. You see the formula same. And now finally, we have, so finally combined together. Finally we have, okay, for if the constant is linear in the general velocity, so we have okay, now once we want to write down here, so I need use the same say the same time to make the make this equation the final version. So we have first, finally, let's do this one. So partial, this is independent of QG, right? It's only this one. So the partial mu alpha g alpha with respect to the QG is equal to alpha from 1 to m mu alpha partial g alpha partial QG, right? Since mu alpha does not depend on QG. Second, this term. This total time due one is to this, because this depends on time, another, so we have two terms, right? T partial alpha partial QG. Now, we go to the first one, is summation to m. Since here you first do the mu alpha with respect to QG dot, but it does not depend on. So then the first one is already is mu alpha partial g alpha partial QG dot, right? So in that case, then you do this first. I do the total time derivative, and I keep partial g alpha partial QG dot, right? Second one is summation alpha from 1 to m. I keep mu alpha. Total time derivative of this one, partial g alpha partial QG dot. Right? So then we can put this two to here, this one to here, and this one to here. Then let's give the final expression of the Lagrange equation for the non-polynomial constraint if this constraint is linear in the generalized velocity. So finally, now it's the formula. Now I'm going to reorganize. Here I put this one as a positive, so this be negative. This one negative, but then put the reconcile, became positive. So now let's do this. So finally, let's give it the final expression. D dt partial L partial QG dot, right? That is the Lagrange equation, the first term. Second term, partial L partial QG, yes. Equal to okay. Equal to let me move I'm going to move minus, let's first this one, right? Minus